Happy morning, dear friends. Here's yours, Dr. Ajanta. Welcome to Demystify with Ajay. Dear friends, in the previous session, we have learned how to distinguish between numerical and categorical variables. Let's move on to understand a few essential concepts of statistics, namely mean, median, and mode. Dear friends, this mean, median, and mode describes the central tendency in some way, and here mean and median are only applicable to numerical variables, whereas mode is applicable to both categorical and numerical variables. And here in this session, we will be focusing on mean, median, and mode for numerical variables, as their numerical interactions usually convey interesting observation. And here, dear friends, mean you can also specify as like arithmetic mean, okay, which measures the weighted center of the variables. And here, let's use the exact, here I have just specified the formula, kindly just observe, this n which uses to denote the total number of entries, and here the index I, it just specify whichever the total number of entries from I to n. And we are just calculating the mean by using this exact formula. Okay, now let me just see it with an example here. And let I just create here anyhow. So this is what our imports, that is the module. I just want to get it imported. And let me just see an example here. So I will generate some 1,000 numbers from 0 to 1 uniformly, that is going to plot here. Okay, by using the histogram, we are just going to make the plotting. And of course, kindly just observe, dear friends, what we are just going to plot is the distribution of an data that we are going to evaluate by that randomly generated function. Okay, so let me just have the histogram first. And this is the exact one which we just to show. But anyhow, let me know the exact value of the histogram, that is the mean value. And here we just go that numpy dot mean function, which we are just calculating. And the mean is around 0.5054. Okay, pretty, it just close to of course, I just expected to be between the 0 to 5. So here it would be just like 0.5. Okay, so it is, which is pretty close to that. Okay, fine. Now, next, let me just move on to the median. What this median measures is the unweighted center of a variable. See, if there is an odd number of entries, the median takes the value of the center one. And if there is an even number of the entries, the median takes the value of the mean of the central two entries. So here median may not be influenced by every entry values on the account of this actually properties. So median is more robust or representative than the mean value. So here let me just take the same set of entries as we have just done here, RVS. Okay, so let I just calculate the median of that same RVS. So kindly just observe what is the result. Of course, the result is 0.5136. See, actually, I will change one particular entry here. Okay, that is 1,000. So here 1,000 is in the sense 1,000 times larger than the maximal possible value. So that is in the database. Okay, so let me just repeat the same calculation of evaluating mean and median here. Okay, so observe. So the result is 1.505, and here the median is 0.515. So what it just is the mean increased roughly by one value, that is whole the things of 1. So the relationship between mean and median is usually interesting and worth investigating. Okay, so usually the combination of the larger median and the smaller mean indicates that there are more points on the bigger value side. So, but that an extremely smaller value also exists. Okay, so the reverse is true. So when the median is smaller, then the mean So yeah, of course, we just make so many examples. Yeah, coming to the later. Now let me just move on to the mode. Okay, so here the mode of a set of values is the most frequent element in a set. So it is evident in a histogram plot such that which represents the peak. That is the mode. Okay. So if the distribution has only one mode, yeah, we call it unimodal. And if we just have some two peaks that don't have an equal heights or which we just specify it as like a bimodal. Okay. Now what we are just going to do is, yeah, randomly let me just take some values. Okay, R1, R2, R3. Okay, and we are just going to plot two things. One is for unimodal and another is for bimodal. Okay, and here each and everything we are just going to make it as a side by side. So subplots I have just specified, and one is histogram of unimodal, and to the same histogram of here I'm just going to make summation of R2 and R3 here. Okay, so let me just view the exact output and kindly just observe here. So see here, this is unimodal where we just have only one peak, but when coming to the bimodal, of course it is not equal. Even though if it is not equal, we have two peaks here. Okay, yeah, so which is that represents the bimodal. Okay, so now let me just move on to the other, and kindly just I want to specify one thing. See, actually this mean, median and mode, there is just an just basic of the statistics of a data set, but almost these are exact main important to start almost all exploratory data analysis. So yeah, let me just jump on to an important part which we are just going to describe. That is these degrees, that is certain degrees is that is the properties of central part of data sets. So here in this we will just describe the spreading behavior of the data. So this mean, median, mode would just specify the center degree, and here we are just going to see the distribution. And this distribution, the first of all let me just see about the variance. Dear friends, actually here I'm just going to have as like a plotting functionality, and here with the same notation I just want to make the variance of that population. So here of course we are just going to see some two differentiation. One is big variance and the small variance. Okay, so what would be the big variance and small variance is yeah, one, let me just make it in the plotting of both the things side by side as like a subplot. And here the larger the big variance, what we are just going to make it is, yeah, let me give the variance as 0.09 variance, and when we just go on to the smaller variance, we are just going to give as 0.009, that is 10 times the smaller. Okay, so let I just plot the first plot the diagram first. So here it is the exact histogram, the same histogram we have just done here. And yeah, kindly just observe how the exact variance. So see, each and every plot whichever we have just plotted, it seems the 10 times smaller the exact distribution here it just shows. You can also have the same thing by using a scatter plot, and kindly just observe, dear friends, actually here I have just specified the scatter plot of the same the two randomly specified variables. Okay, and let me just plot here, and here I just want to make one more thing, dear friends. Actually whenever we just make use of this exact ranges, this exact xlim would just show what is the range of the distribution. Okay, so it just determines the ranges. So first of all let I just plot it, and kindly observe here how it happens. So yeah, of course, in the x-axis, kindly just see the spread of data, which is in the x-axis is significantly larger the spread of the y-axis. So which indicates the difference in variance magnitude. See, actually a common mistake is not getting the range correct, but here the matplotlib will be by default try to determine the ranges. That is what we have just specified by xlim, that is plot.xlm, just to force it to limit the exact ranges. Okay, yeah, of course, otherwise the exact result would be misleading. So that is what we have used it, and yeah, by that we have identified that is the x-axis has the higher the spreading compared to the y. Okay, now let's move on to the standard deviation. Dear friends, standard deviation is the square root of the variance. So it is used more commonly to measure the level of dispersion, since it has the same unit as the original data. Okay, so this standard deviation is extremely important in scientific graphing. So a standard deviation is often plotted together with the data and represents an estimation of variability. Okay, so let me just take, of course, I have already included the data set in the first itself. I just scroll here. Yeah, so see here the same thing we have already included as the data set, and yeah, we are just going to make use it in the standard deviation. So here, of course, what is the data is, yeah, it is all about the net immigration rate for Texas from 2011 to 2018. And this first extract the country level alone, the state level data, okay, and appends the means and standard deviation. We are just going to add it, okay, and append it, okay, the means onto the list, and then plot them at the end. Okay, so we are just going to make it appending by each and everything, and we are going to plot it by using the error bars. And here this error bar is plotted using matplotlib pyplot. Okay, so here we have just specified as pyplot as plt, and by using this error bar we are just going to see how the standard deviation has been added. So let me execute it and kindly observe here. Okay, so here you can see the exact figure. So although the net immigration is Texas is only slightly positive, so only slightly, whichever here it is 0, so slightly positive only we can just get it. The standard deviation is huge. So some countries may have a big positive net rate, while some other has potentially which we suffers from a loss of human resources. So there it just takes the positively huge. Okay, so here of course only slightly positivity it just shows, and of course we extracted only the Texas data here. So that is what here it just specifying. Okay, now next moving on to the quartiles. Okay, dear friends, actually these quartiles are a special kind of quantile that divide data into number of equal portion. So for an example, this quartiles divide data into 4 equal parts. So with that half quartile as the median. So this decile and percentile divide data into 10 or 100 equal parts, which is which we already specify like that. Okay, the first quartile always be known as the lower quartile, that is Q1, which it just takes the value as 25%. And the second one would be the median, and third one Q3, which is also known as the upper quartile, and which we just shows the 25% of the ever remaining. Okay, so let me just execute the quartile first. Okay, and here we just have the 3 quartile which we are specifying 0.25, 0.5 and 0.75. Okay, so let me just have it as like an array. So this is the exact value of that quantile functionality. And yeah, let me make the same thing by using the histogram. Okay, so let me plot it. Okay, by using the plotting, how we are just making this. So this quantile, numpy.quantile, though this is the exact function, we can specify list of quantiles as like an argument. Here we have just passed it. Okay, and we have calculated the exact quantile thing, and when on passing the same thing, yeah, we can make it in the output. And towards this output, kindly just see 3 vertical dotted lines we are able to see that indicates the 3 quartiles. And here the lower the quartile, of course, here we just have, this is the higher quartile, that is upper quartile, and kindly exactly see that 50% of the data which we just specify the median. Okay, so here the Q3 towards Q1, which is referred to as the interquartile range, which we just say IQR. Okay, so that plays an important role mainly in the outliner deduction, and of course we are just going to discuss what is outliner in a separate video. Okay, yeah, now next we are just moving on to the skewness. Dear friends, this skewness, it just differs from the three measures of variability which we just discussed in the previous thing. Okay, actually it measures the direction the data takes and the extent to which the data distribution titles. So here this skewness is unitless. So if the mean is larger than the mode, skewness is positive, and we say the data is skewed to the right, and otherwise the data is skewed to the left. So let we just here, of course we are just going to take three set of values. Okay, so let me just make use of plotting of two subplots. I just want to make it into subplots, and randomly how for we are just taking r1 plus r2 here and r1 plus r3 as another plot. And yeah, because we have to show something skewness, no? So I just purposely done this. So let me just plot the two things. Kindly observe here. And of course, the exact dotted line, the vertical dotted line indicates the position of the mean of the exact data set. And kindly observe whatever the data points that lies onto the right. So here towards the right of the x and y axis. So that specified the skewed to right. So this is rightly skewed. And if it is higher than to that of mean value, so higher to the than that of the mean value, so it is higher than the mean value, so which it just specifies skewed to the left. Okay, so yeah, of course you can also specify this as like when we just specify the right skewed, yeah, it is specified as like a negative skewness. You can just see, yeah, the data which is passing to the negativeness. And of course you can just say the left skew, the which is skewed left, so it is also indicate as like a positive skewness. Okay, which is in here this negative skewness just indicates that the majority may have the functionalities in the negative side. And here when we just go towards the left, that is positively skewed, yeah, more the data that are lies onto the left, that is positive data. Yeah, dear friends, of course here we end with the numerical data. In next video, let me just discuss related to the categorical data. And dear friends, if you want to take your learning to the next level, join us on the exciting journey. Yeah, don't forget to hit the subscribe button and turn on the notification bell. Stay updated with our latest uploads. Thank you, dear friends. Happy learning.